In this session, we will be discussing about transient heat transfer, which is also known as unsteady heat transfer. So what is a transient heat transfer? If the temperature is changing with respect to time, then it is known as transient heat transfer. This can be expressed as dt by dt is not equal to 0, where tau is time. So I will make it similar. Consider a plane wall, and the temperature at this point is, let's say, that is 30 degrees Celsius, and at this point the temperature is equal to 25 degrees Celsius. Make it T1 and T2. So this is the temperature drop. So this is measured at a time, initial time as 0 second, and after 5 seconds, if it shows the same temperature 30 degrees Celsius and 25 degrees Celsius, which means it is at steady state. And if the temperature is varying after 5 seconds, the temperature is varying to 33 or 34 or 25, and here also temperature is varying, then it is unsteady state. That means the temperature is varying with respect to time. Now we are going to analyze the heat transfer equation in transient condition and find out or formulate an equation for temperature distribution and heat transfer. For that, we can consider a slab with thermal conductivity K and its length L and its cross-sectional area is A. Our aim is to formulate an equation to find out the temperature at any time for this slab. Okay, this slab is at room, which means this slab is surrounded by the room air, which is at a temperature TA. TA is the ambient air temperature or room air temperature, and in this case we are assuming that the room air temperature is less than that of the slab temperature, which means slab is having more temperature than the atmosphere temperature. So, and in this case the heat is transferring from the plate to the outside. The heat Q is transferring from the plate to outside. Now we know that the heat balance equation as Q in minus Q out is equal to change in energy, or in we can represent it in a rate form also. So here there is, for the slab, there is no Q in, there is no heat is coming into the slab, and the Q in is 0, and Q out, of course it is some heat is transferring from the slab, so Q out is there, and delta E we can also, this is MC d T by d tau. We already discussed this in our previous modules. So minus Q out is equal to MC dt by d tau, twice time again. So Q out is equal to minus MC dt by d tau. Q out is equal to minus MC dt by d tau. Okay, then what is this Q out? Q can be conducted plus Q can be convected. Q can be conducted and Q can be convected from the slab to outside air. So let's go to the conduction equation. General conduction equation we already studied in the first module. So let's write what is general heat conduction equation. Dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Qg by K is equal to 1 by alpha dou T by dou tau. So in this case we are only this, in this slab the heat is transferred in one dimension, so we can, all other direction we can assume it as 0, and there is no heat generation within the system, and this is also equal to 0. Of course this is there. So if you take the conduction equation, the equation becomes dou square T by dou x square is equal to 1 by alpha dou T by dou tau, which means In order to solve this equation, we require here, this is a second order equation, that means two boundary condition here and one boundary condition here. Total we require three boundary condition equation. So for the analysis, to make the analysis similar, we will not consider the heat conduction, which means dou square T by dou x T by dou x square is equal to 0. Okay, that means the temperature is constant through it. So this is our slab and the temperature is not varying, temperature is a constant throughout the location, and this is temperature is uniform. If with respect to the location the temperature is not changing, we can say that it is a uniform temperature condition. And this will give another point, the conductive resistance L by Ka, conductive resistance L by Ka, or it is also known as internal resistance, internal resistance. So this L by Ka value is 0. This L by Ka value is 0. If the temperature is uniform, if the temperature is not varying with respect to x or with direction, L by Ka should be 0. That means we can assume this condition only if L by Ka is equal to 0. When L by Ka becomes 0? L by Ka becomes 0 only if the value of K is very high. So this assumption can be only made for the material with high thermal conductivity. And the approach or analysis in which the L by K value or internal resistance is neglected is known as lumped parameter analysis. Lumped parameter analysis, very important. Okay, going back to our heat balance equation. Now we have the heat is only convected. Okay, and this is our slab. From the slab, the heat is only convected to the surrounding. It is only convected to the surrounding. So I can rewrite the equation as Q convected is equal to minus mc dt by d tau. This is mass. Mass can be written as minus rho into volume. C is the specific heat capacity, dt by d tau. So Q convected is equal to minus rho Vc dt by d tau. Q convection means what is convective resistance or surface resistance? 1 by HI. 1 by HI is present here. The 1 by HI value is not is equal to 0, whereas L by Ka value is 0 in this analysis. And the temperature of the plate is T, because the temperature is not changing, the temperature is constant throughout the x direction. So temperature we can take it T is the temperature of the slab, T is the ambient air temperature, and Q convection is equal to minus rho Vc dt by d tau. Then what is Q convection? By Newton's law of cooling, Q convective heat transfer is equal to H into area, that is surface area, into delta T, the temperature difference. What is the temperature difference? T, the temperature of slab minus ambient air temperature, is equal to minus rho density V volume C dt by d tau. On rearranging this equation, we can have HIS surface area by rho Vc, minus sign is here, dt by d tau is here, dt by T minus Ta. So we have just rearranged the equation. HIS minus HIS by rho Vc d tau is equal to dt by T minus Ta. Now the next step is very simple. We can integrate it this is the integration. We can integrate d tau and we can integrate, this is a variable separable form, so we can integrate it. So on integration we will get LHS side, we will get minus HAS by rho VC d tau. On integration we will get tau is equal to dt by t minus ta. It is log t minus ta. So I am adding a C1 here, I am adding a C1 here, that is a constant. So on rearranging, I am rearranging this equation as log t minus ta is equal to minus HAS rho VC tau. Okay, I am adding a C1 again here. Okay, once again I will explain. This is the equation we have got. This is a differential equation, first order, and then we integrate it after separating the variables, and now we have got the solution as this. C1 is the arbitrary constant, so we have to find out the value of C1 by applying boundary condition. Then only the solution is completed. Boundary condition. So there is only C1, which means we require only one boundary condition. That is why we reduce it into this form. So what is that boundary condition? One boundary condition. Okay, this is a transient heat transfer, so the boundary condition must be related to the transient condition. The boundary condition is the temperature, the initial temperature T is equal to Ti. I represent initial temperature at tau is equal to 0. Tau is the time. At tau is equal to 0, the temperature is equal to Ti. I am going to apply this boundary condition into this equation. Log T minus Ta is equal to minus HAS by rho Vc tau plus C1. So when we apply tau is equal to 0, when T is equal to Ti, tau equal to 0. So what is remaining? Log Ti minus Ta is equal to C1. So we have got log ln log Ti minus Ta is equal to C1. So the solution is log T minus Ta is equal to minus H into As divided by rho Vc tau plus, we know what is the value of C1, log Ti minus Ta. Again to rearranging, there is a log term, there is another log term, we can combine it together. Log T minus Ta divided by Ti minus Ta is equal to minus HAS by rho Vc tau. So I can rearrange as T minus Ta by Ti minus Ta is equal to e raised to or exponential of minus HAS by rho Vc tau. This is the temperature distribution equation for a lumped parameter analysis. So T can be expressed as T is equal to Ti minus Ta. Okay, I can write in as e raised to minus HAS rho Vc tau plus Ta. This is the temperature distribution equation, temperature equation, distribution equation. So using this equation we can find out the temperature at any time. If we put a value for tau after 5 seconds, what is the temperature? If you know the initial temperature and ambient air temperature, we can find out the temperature at any time. Okay, now we can discuss more about the quantity HAS by rho Vc. So for that we can first analyze what is the unit of HAS by rho Vc. HAS by rho Vc unit. So unit of H is equal to watt per meter square degree Celsius, and the unit of surface area AS is equal to meter square, and divided by rho is equal to mass by volume, kilogram per meter cube, and volume is here meter cube, and C joule per kilogram Kelvin. So all the meter cube cancel, meter square cancel. Okay, degree Celsius, make it Kelvin. So make it Kelvin, and then kilogram cancel, and the remaining is watt per joule, and that is joule per second per joule, that is 1 by second. The unit is equal to 1 by second. Okay, then very interestingly, the unit of rho Vc by HAS is equal to second, the same unit as unit of time, and this is known as, for the quantity rho Vc by HAS is known as thermal time constant. It is known as thermal time constant, and this quantity rho Vc by HAS is represented as tau Th. It indicates the rate of response of a system to a sudden change in its environmental temperature. Now we can discuss about the quantity HAS by rho Vc into tau. HAS by rho Vc into tau. Of course, this is a dimensionless quantity because dimension of tau is equal to second, and dimension of HAS by rho V is equal to 1 by second. So this is a dimensionless quantity. So I am doing some rearrangement for this quantity, that is H into AS into rho into Vc. Okay, into tau. Area by surface area by surface area. Okay, then volume by volume. This is just for a rearrangement. Thermal conductivity by thermal conductivity. The value is not varying, multiplying and dividing by the same quantity, surface area into surface area, volume by volume, thermal conductivity by thermal conductivity. Now I am just rearranging this equation, rearranging the terms. H into K by surface area into V, that is V by surface area, into surface area by V square into K by rho C into tau. Just rearrangement only. Just go through this, you will understand the rearrangement also. So this quantity volume by surface area, the quantity volume by surface area is known as characteristic length. Characteristic length. And it is represented by LC. This is characteristic length represented by LC. So I can rewrite this equation HAS by rho Vc as HAS by rho Vc to as H by K LC into K by rho C is alpha tau into LC square. So now we can write the quantity. Now we can write the quantity HAS by rho VC tau as the product of two quantities HLC by K into alpha tau by LC square. And this is also a non-dimensional quantity, and alpha tau by LC square is a non-dimensional quantity, and the quantity HLC by K is known as Biot number, which plays very important role in transient heat condition. Biot number. And alpha tau by LC square, this is Fourier number. So you might have seen this number in your convective heat transfer, HL by K, that is Nusselt number. So the only difference is that Nusselt number is for a fluid, here it is for a solid. Okay, please keep it in mind. HLC by K, it is known as Biot number. So what is this Biot number, what is this HLC by K? Biot number is the ratio of internal resistance to the surface resistance. So what is internal resistance? Internal resistance is also known as conduction resistance. So Biot number is the ratio, for simply BI. Biot number is the ratio of internal resistance L by Ka to the surface resistance 1 by HA. So what is remaining? HL by K. When I discussed about the lump parameter analysis, I have said that for a lump parameter analysis, the internal resistance is assumed to be 0, which means L by K is equal to 0. I said it already. So for that, for a lump parameter analysis, L by K is equal to 0, then Biot number is equal to 0. For lump parameter analysis, the Biot number should be 0. But this is not a practical situation. It cannot be a 0 value. So for the lump parameter analysis, we are having a condition that if the Biot number is less than 0.1, we will consider that case as a lump parameter analysis, lumped analysis. So this is a checkpoint. If you get a problem or scenario related to the transient heat conduction, first you should do the calculation HLC by K, and if the value is less than 0.1, you can go for the lump parameter analysis. And what if the value is more greater than 0.1, that I will discuss. We can discuss about that later. And Fourier number alpha tau by LC square, it signifies degree of penetration of heating. And now we can write the temperature distribution equation, T minus TA minus Tim minus TA is equal to e raised to minus Biot number into Fourier number. Okay, this is the temperature distribution equation in terms of Biot number and Fourier number. Okay.